In this lesson, we are going to solve a series circuit, and this is the same process you're going to use for all of them. And when I say solve a series circuit, what I mean is we're going to find the voltage drop across each resistor, we're going to find the current through the circuit, and we are going to find the power of each resistor and of the battery. And we'll do a couple checks along the way to make sure everything's making sense. Now, the first step is always going to be finding the total resistance. Remember, in a series circuit, that's easy. We just add up the individual resistors. Then we're going to use Ohm's law to find the current leaving the battery. Once we know that, that's the current through everything. Okay, this is current everywhere because in a series circuit there is only one path, so whatever current goes into something has to come out of something. And then we apply Ohm's law to each individual resistor to find the voltage drop across that resistor. Then we'll know the voltage and the current in each resistor, and we can find the power. So let's start with a nice simple series circuit. We're going to have a 30 volt battery, 30 volts, and we're going to hook it in series to a 12 ohm resistor. We're going to call that R1, and we'll go around our loop and we'll hook it to a 3 ohm resistor. We're going to call that R2. Okay, so R2 is 3 ohms, R1 is 12 ohms. First step, find the total resistance. So RT is 3 ohms plus 12 ohms, which equals 15 ohms. Now we can do step 2, which says, hey, let's find how much current is actually moving in here. So step 2 says use Ohm's law, V equals IR applied to the battery. So that's V equals 30, I equals unknown, and R is 15 ohms because we just found it. We can divide both sides of this equation by 15 and get that our current is 2 amps. Now, because it's a series circuit, that 2 amps flows out of the battery and goes through every single resistor and back to the battery. So our third step is just to apply Ohm's law to each resistor, right? We know the current in every resistor. We just now have to find the voltage drop across each one. So we'll start with R1. R1 equals 12 ohms, and the current is 2 amps. So the voltage drop across that, V equals IR, that's Ohm's law, is 2, that's amps, times 12, which equals 24 volts. So 24 volts of potential energy per charge is dropped, or converted really if you'd like, into heat by that resistor. And then we can do the same thing with R2. R2 is 3 ohms, and its current is 2 amps because remember the 2 amps went in, 2 amps came out, 2 amps go in, 2 amps come out. And so same thing, V equals IR, and we get 3 times 2 is 6 volts. Now a couple things we should look for to make sure that they add up. This is the voltage drop across this one, that's 6 volts. The voltage drop across this one we found was 24 volts. Together, those two add up to the 30 volts of the battery, which is good. Energy is conserved. Not only that, if we want, we can find power. Remember, power is simply voltage times current in the circuit. And so if we wanted to do that, P equals VI, well, the power of resistor 1 would be the voltage across it, 24, times the current through it, 2, which is 48 watts. And the power for resistor 2 would equal the voltage drop across it, 6, times the current through it, 2, which is of course 12 watts. Now together that means we are dissipating energy at a rate of 60 joules per second in this circuit, right? 48 plus 12 is 60. That better be what we're generating over here in our battery. Well, the power of our battery is equal to the voltage of the battery times the current through the battery, which is still our 2 amps. And so this is 30 times 2, which is in fact 60 watts. So we do see that, just like we expected it to be, energy is conserved. We have power being produced at 60 watts over here and then consumed at a total of 60 watts in the circuit.